Hi, this is Cynthia Taylor, and today I'm going to be talking about the practical details of building a CS concept inventory. So this is going to be an experience report on our experience building the basic data structures concept inventory, a project that's taken us the last 6 years. And this is joint work with Michael Clancy, Kevin Webb, Dan Zingaro, Cynthia Lee, and Leo Porter. So first of all, what is a concept inventory? Well, a concept inventory is a validated assessment which is designed to measure student learning of the core concepts of a subject. So unlike something like a final exam, we don't expect this to measure everything that you cover in a course, and we don't expect it to be a lot of, let's say, equations, plug and chug, things like that. Instead, we're really trying to measure, do students understand the fundamental concepts in a particular subject area? And validated simply means that we've spent a lot of time testing to make sure that this actually measures what we think it measures. So the value of a concept measuring is it allows us to measure whether or not our students are learning. So that lets us look at changes in curriculum, changes in educational practices and things like that, and say, okay, if I adopt this new educational practice in my class, are my students actually learning more? And notably, they've served as a catalyst for vast pedagogical change in other STEM fields. So the force concept inventory in physics caused a huge amount of change in how physics is taught, as it caused professors to realize that their students actually weren't learning what they expected them to. So currently in computer science, we have 2 concept inventories available. So these are the SCS1, which covers computer science introductory concepts, and the digital logic concept inventory, which covers digital logic. So we only have 3 concept inventories available to us right now, including our new concept inventory, the basic data structures concept inventory. But this is an area in which we've seen a lot of interest and a lot of preliminary work in recent years. So we've also seen preliminary work in algorithms, recursion, advanced data structures, computer architecture, and operating systems. And of course, we hope that all of you will go out and make your own concept inventories after you see this talk. So our concept inventory is the basic data structures inventory, or BDSI. So it covers basic data structures. It covers array lists, stacks, queues, linked lists, binary trees, and binary search trees. And with these data structures, we're specifically trying to look at, can students do the following? Can they analyze the runtime efficiency? Can they select appropriate data types for a specific application? Can they compare trade-offs between data structures? Can they design and modify data structures? Can they trace through and predict the behavior of an algorithm, including tracing through and predicting the behavior of code? And can they identify and remedy flaws in a specific implementation? So can they debug a specific code for a data structure? So to develop this data structure, we started off looking at Adams and Wyman, who have 6 classic steps that they suggest to develop a concept inventory. And these are steps that have been used by 6 or 7 existing concept inventories in the STEM fields. So their steps are this. They first talk to instructors in a specific area to establish the topics that are important to them. Then they have selected interviews and observations of students to identify how students think about these particular topics and the ways in which it does not agree with the way experts think about it. So based on these interviews, they then create open-ended survey questions to probe student thinking and try to turn it into an open-ended test to really figure out what are students getting wrong here. Based on this open-ended test and the student answers and misconceptions, they then create a forced answer test that measures student thinking on this. So this becomes the concept inventory. And then with this forced answer test, they can carry out validation interviews with students as well as experts on the test questions, and they administer the resulting concept inventory to classes and run statistical tests on the result. So we followed these basic steps with a couple tweaks. So the first thing we did was that we combined their steps 2 and 3. So instead of interviewing students to find out where they deviated from expert thinking, we relied on our existing knowledge of student thinking, including one of our team members who had 20 years of experience teaching data structures. And so based on what we already knew, we developed a set of open-ended questions on these topics. And then in our interview stage, we not only interviewed students, but we also administered a large number of open-ended practice exams and coded the answers that we collected from those practice exams in order to discover misconceptions, which then became the multiple choices or distractor answers in our multiple choice version. And then once we had done that, we carried out validation interviews and we statistically validated our concept inventory. So our first step was building a team. Our key team was the team of researchers that you saw at the beginning as the authors on this paper. However, our backgrounds are mostly skewed towards research and selective liberal arts schools. And so to help us, we created an expert panel of 8 other people who had large experience teaching data structures. And we tried to select these people to represent a variety of institutions. So we selected for both large and small institutions, research-focused versus teaching-focused, community colleges, and so on. And the final member of our team was our outside evaluator. So she was an expert at building concept inventories, but she was not a computer scientist. She was someone from chemistry. So what did we learn from our experience building a team? Well, the first thing we learned is that it's really, really valuable to have an expert evaluator who has experience building concept inventories. Throughout our experience building this concept inventory, we would worry that we'd done something wrong or have a question about the right way to proceed and so forth. And she was always there to help us or to put us in touch with someone who could give us answers to our queries. So we really recommend having an outside evaluator who is an expert on concept inventories if you're taking on this kind of project. Our second lesson we learned was to select a team of experts that all go to SIGCSE. So we've been meeting our team of experts here once a year, and it's been really great to know that everybody will be at the same place at the same time once a year. We can corner them for half an hour and an hour and get their feedback on something. So creating a team that you know will all be at the same place at the same time is really great. And then lastly, we had to remember that professors were extremely busy, and we tried as much as possible to value the time of our experts and to only come to them when we really needed their advice. So our first step in the classic Adams and Wyman steps were to establish topics. And so in order to do this, we first collected and reviewed course syllabi and exams from as many people as we could. So this included all of our course syllabi and exams, as well as those from our expert panel. And reviewing these, we found 49 subtopics that we grouped into 6 topics. So here a subtopic would be something like, something like inheritance, or say linked lists. A topic would be something like object-oriented programming or basic data structures. And what we found was that no single course covered all of these topics, but one, basic data structures, was covered in every course we looked at. And so we narrowed the focus of our concept inventory to only look at basic data structures. So we looked at our basic data structures subtopics, and we converted these subtopics into 11 learning goals. We then took these 11 learning goals to our expert panel, we modified them, we got their feedback, and we consolidated them into a list of 6 learning goals. So what did we learn from this? Well, the first thing we learned was that many of our original goals were something like implement insertion into, location in, and deletion from a binary search tree. And then we'd have a second goal that would say implement insertion in, location in, deletion in a linked list. So we took all of these goals and we revised them to be of the form design and modify data structures capable of insertion, selection, and search and related operations. So essentially, we resulted in 6 broad learning goals that could apply to any data structure, and then a list of data structures that we applied them to. The other thing that we saw when establishing topics, where there's a lot of contention about whether students should be able to select an appropriate interface select an appropriate implementation, or implement a data structure themselves. And we ended up going with all 3 of these, and these became our first 3 learning goals. So our second step was to develop a set of open-ended questions. And so in order to do that, we collected short answer exercises from all the exams that we had collected. We also took 2 exercises from Piers and Wolfman in their previous SIGCSE paper. And we also took questions from our own CS2 course material. And as I previously mentioned, one of our team members had 20 years of experience teaching this class, so he had a lot of material. And using these open-ended questions that we had collected, we conducted 1-hour think aloud interviews where students worked through these problems while we observed them. And we did this with 50 students across 3 different institutions. And the important thing was we needed students who had recently covered all of the relevant material, which meant that we really only had 2 weeks at the end of a term to interview, because we needed them to be almost at that final exam, but not to have finished the course and gone home and forgotten it all. And so what this meant was that we really had a really limited period to do our interviews, and at the end of that we would have to wait an entire other term before we could interview again. And lastly, we paid our students for their time with an interview with an Amazon gift card in exchange for sitting through the interview. So what did we learn from this? Well, the first thing we learned is it's surprisingly difficult to get students to show up for interviews, even when you are paying them to be there. So our best practice ended up being to have them email us to confirm they still wanted to do the interview, to email them a reminder the night before, and then we still had 10 to 20% of students who didn't show up. So definitely plan on booking more students than you actually need, because you can expect a 10 to 20% dropout rate. We also found a tension between covering all of our goals and having an exam that could still be administered in 50 minutes. So it was important to us that any professor be able to give this exam in a standard class time period, which meant that we couldn't cover every goal for every data structure. So we do cover all of our learning goals and all of our data structures, but not every single data structure with every single goal. We also found it extremely difficult to keep track of different versions and questions and exams. We were continually revising both our questions and the set of questions that we administered at one time. At one point here, we had 2 distinct question 33s, one of which we referred to as Dan 33. So we definitely recommend that you invest in some sort of organizational system here, because it's extremely difficult to keep track of, okay, what's the latest version of this particular question and which questions are currently on the set of questions I'm giving to students. We also discarded far more questions that ended up making it on our concept inventory. So we developed 43 questions and only 13 of them ended up on the finished CI. So we recommend developing and testing a large number of questions. So step 3 was to convert our open-ended questions into multiple choice questions. So in order to do this, we needed misconceptions to provide our distractor answers. And again, we used student interviews. We also gave open-ended tests to study sessions, during study sessions to 408 students at 2 different institutions. And once we had these, we coded their answers to look for common misconceptions. So we went through all of the student answers and grouped them into common wrong answers. And these common wrong answers became our distractor answers for our test. During this time period, we also met with our expert panel twice and showed them our current set of questions and the distractor answers. And we asked them both, would you consider this a reasonable question for your students? Do you think your students would be able to answer this question? And also, do you think this question is important? Do you care if your students are able to do this? And only if they agreed with both of those questions did the question end up going on our final version of the exam. So what did we learn during this? Well, first, when you look at the Adams and Wyman steps, or our steps, it's easy to believe that these are all separate categories. Like first we develop all of the open-ended questions, then we develop all of the multiple choice answers, and so on. But actually we found that these processes all overlap. So development of open-ended questions, development of multiple choice answers, and finalization of wording were all an overlapping process. And as we were giving out these practice tests to exams during these study sessions, to students during these study sessions, frequently we would have some open-ended questions, some multiple choice, some almost finished questions, and so forth. The second thing we discovered was that the process of converting questions from open-ended to multiple choice basically converts someone from an application question to a recognition question. What this meant was that all of our questions for our right code for this data structure goal became very similar to trace and predict the behavior of algorithms questions, because we're giving them multiple choice answers and they could essentially trace all of the answers to try to figure out which was correct. We also found that sometimes questions that were frequently wrong answers for open-ended questions were very rarely selected in our multiple choice version. So for example, when we gave students a question about doing recursion on a binary tree, what we found in the open-ended question is frequently they would make a mistake where they would check if the right child of the binary tree was null, and if it wasn't, they would return the recursive call for that right child and never actually go on to the left child. So we saw this mistake a lot in our open-ended questions, but when we converted it to a distractor answer for our multiple choice questions, students basically never selected it. And we think that's because they could look at the other choices and see that that answer was clearly wrong, and they didn't have that option when they were doing it as an open-ended question. So step 4 was our validation interviews. Our goal with this was to make sure that students were correctly interpreting our questions. Did they interpret the question that we were asking the same way as we did? And why were they selecting a specific answer? So were they selecting the right answer because it was actually right? Or were they selecting it because it was the longest answer, and so forth? So again, we held a lot of interviews. We held 2 different rounds. This is of course across a year, since we had to wait multiple terms between rounds of interviews with 49 students across 5 different institutions. And again, we were really trying to make sure students from different populations all answer this the same way and make sure that it wasn't skewed towards any particular population of students. So in these interviews, students worked their way through the entire concept inventory while thinking aloud, so while just narrating why they were making the choices that they were. So what did we learn for this? Well, we learned that a lot of our questions were flawed. First of all, we discovered a lot of questions that needed significant rewording. We also discovered questions with fatal flaws. So one example of this is that we had a question that was, imagine a data structure that stores items as a key value pair, where the key is an integer value that can be negative. Choose the data structure that will provide the best performance for implementing a get method. So what we imagined students would choose as the correct answer was either a binary tree or a array that they could search using binary search. And we imagined their time for all of this would be O log n for both of those. However, what we found was both very strong and very weak students were choosing an array as the answer, and they were claiming that it had constant time. And what was happening was that very weak students were just assuming you could index into the array with a negative integer value, whereas very strong students were saying, oh, we can just add an offset to all of the keys in our array. So if our lowest integer value key is negative 100, we'll just add 100 to everyone, and we'll just make a really, really big array. And so we tried rewording this question over and over and over again. We never found a rewording that avoided this problem, and we ended up significantly changing this problem. So our last step was statistical validation. Our expert evaluator was really invaluable here. She gave us a lot of good advice on how to proceed with validation. We were also very inspired by recent work at SIGCSE by Z et al. So for our validation, we used both classical test theory and item response theory, and we administered our tests at 8 different institutions. However, we ran into a problem in that only 4 of these had enough responses for actual statistical validation. And so our smallest run that was big enough for statistical validation was 64 responses. What we did was we combined these with 64 randomly selected tests from each of the other 3 institutions. And that's the sample that we ran our statistical validation on. So what did we learn? Well, we found it's difficult to both represent all types of institutions and meet statistical sample size requirements, since some institutions by nature end up having small class sizes. We also found that the literature is still very mixed about which statistical test to use. So we did our best to choose the ones that we felt would represent our arguments well, and we tried to explain why we chose each of these tests. So if you're interested in administering the basic data structures inventory, it's available at the following URL. It's a Google group. We'd love to have you join it. We'd love to have you try this in your test. And we will say that this is validated only as this specific set of questions with this specific wording. So we recommend you don't change it because we can't make any promises about its validity if you do. So thank you very much. I'm happy to answer any questions by email. And thank you for your time.